Okay, today we're just going to quickly review distance time graphs, and then we're going to look to see how velocity time graphs work. So yesterday we did distance time graphs. Let's just quickly go through that. So if you have, in this case, the first orange section there, we're going from a distance of 0 up to 3, and our time is going from 0 to 3. So remember, a slanted line like that is the slope of the line is going to be the change in distance over time, which will basically be distance over time, which is what we figured out the other day is our velocity. So when you have a slanted line, our velocity is just going to be the rise over the run. So in this case we'd have a change of 3 over 3. So we have a velocity of 1 meters per second. Okay, then remember the green sections. So the next ones we just have flat lines. So that means we have no slope. So that means we have no velocity either, right? We are just at 0 meters per second for both. So the object is stopped during that time. And let's leave the blue one for a second. The yellow one is a downward slope. So it makes sense that it is velocity again, but now it would be negative. So in this case, if you look at the distances, we're going from a distance of 1, 2, 3, 4, 5, 6 up, and we're going down to a distance of 2 below. So we ended up from -2, so we're ending at -2. We subtract 6 above, and that occurred over 1, 2, 3, 4, roughly 5 seconds approximately. So that means we have -8 over 5, which would be a velocity of about -1.8 or 1.6 or something like that. I'm going to cheat a little bit. Let's make our time a little bit shorter. So then we'd have a time of 4 seconds. So 8 divided by 4 would be -2. Okay, so if you look at the two slopes, the red one is 1 meters per second because it's slanted upwards, and you can see the yellow one is -2. It's a steeper slope but going downwards. So in this case the negative just means we're changing direction. Okay, our velocity slope, if it's upwards to the right, that's a positive velocity, so our distance is getting further away. If it's a negative slope, it's slanted downwards. It just means we're going in the opposite direction. So in this case we were at 6 and we went in the opposite direction down to about -2. The blue section I intentionally left out. Remember yesterday we looked at if you have a curve that's blue, what happens is we get acceleration, right? Because our velocity is changing. It's not at a steady rate. So in this case you can see our distance is getting faster and faster, or we're further and further away as time is getting shorter. So if it was a steady rate, that blue line would be slanted, and because we're getting more distance over less time, you can see it gets curved. So that's our acceleration. And we could also think of it as what would happen if our distance was getting less and less as time went on. So you'd see that straight line would start to flatten out if we accelerated in a negative way. We started to slow down. So if our speed was slowing down but we're still going in the same direction, we'd get an acceleration curve like that. If we're speeding up, it would be the first one that we have drawn there. So either of those cases we have acceleration. We're still going forward. So in both of these that I just showed you, they're both going forward. Just the first one is speeding up, the second one would be slowing down. Okay, so both of those are acceleration. And what I want to do next is just quickly go through the acceleration curves. There's 4 different scenarios. So the ones that we just looked at, so this first one was our speed. We were speeding up and going in a positive direction. So a good way to do this is to look at a little chart. So if we do speed up or slow down, that's our 2 options. So, oops, slow down. And then we'd have forward and backwards would be our direction. So let's assume forward is our positive direction and backwards would be our negative direction. So forward or backward. Okay. So the first one that the blue one is showing is we're going in the positive direction. So that's like the one we just showed. We're going forward and speeding up. So we have positive acceleration, right? Because we're speeding up and we're still going forward. So a positive and a positive would mean positive. So that first one is a positive acceleration. So we're speeding up and going forward. The second one that I drew on the previous page was the red one. So that one you can see we're still going forward, but we're now slowing down. So the curve goes like that, so you can see that we get a negative acceleration out of that one. Okay, and now the other two, the last two would be what would happen if we were going in the opposite direction. So we're going backwards and either speeding up or slowing down. So the first one, if you're going backwards and speeding up, so that would be the yellow graph, because you can see we're going downwards and we're speeding up, so you can see the curve gets steeper and steeper as it goes downwards. So that would be, if you think of backwards as being negative and slowing down as being negative, so we'd have backwards speeding up would be negative times a positive would be negative, and the last one we've got backwards and slowing down. So that would be the green one. So you can see we're going backwards and we're getting less and less, so our time starts getting stretched out. Okay, and because we consider those being negative, backwards direction and slowing down, just like math, you can think a negative and a negative makes a positive. So anytime you have those acceleration curves, you have to worry about it being positive or negative, and there's two parts to it, whether you're going forward or backwards and whether you're speeding up or slowing down. Graphically speaking, the easiest way to remember that is just sort of think if you have a happy face or a sad face. So if you look at the positive ones, we got the blue one going this way. So our first scenario, we had the blue graph going like that, and we had the green graph going, oops, the green graph was going like that. So we get both of those two are positive, and you can see either one of them makes sort of a happy face. So we have positive there, we get sort of our happy face. And then in terms of the graph, if you have either of the two negative ones, you can see they make sort of a sad face. So we have a negative one like that, or a negative one like that. So those two graphs give you sort of a sad face. So that's an easy way to sort of remember in terms of the graph whether it's going to be positive or negative acceleration. These graphs only apply to distance time graphs, because for acceleration on a distance time graph we get a curve, and that's what the four scenarios would be. So today we're going to do velocity time graphs, and you're going to see the graphs are going to look a little bit different. And what you have to be aware of is our scale now is talking about velocity. So this side of the graph is in meters per second. So we have 1 meters per second, 2 meters per second, 3 meters per second, and so on. So the first section on here, you can see it's just a flat line at 3 meters per second. So using common sense, that means we have a steady speed. So for this graph, we had 3 meters per second. If you think back to the old graph, so on a distance time graph, if we had a velocity of 3 meters per second, that was a diagonal line, something like that. And on this graph now, you can see if we have a constant 3 meters per second, it's now a flat horizontal line. So that's a good way to kind of compare the two. The next section of the graph you can see on here is, you can see is this flat part here. So that's at the 0 line, so that means our graph is stopped. So on this graph we have 0 speed. Okay, so for that one we'd have our, let me draw it in black, so we'd have our grid. So a zero line on the grid will just be a horizontal line right on the origin, And if we think back to the other ones, if we had zero velocity, that was a flat line anywhere. That meant we just stayed at whatever distance we were. Okay. The third section that's on here is a flat line. So you can see our velocity is going from 0 up to 4, and you can see that's occurring over 4 seconds. So just like on the distance time graphs, when we had a straight line, that was velocity. So now on a velocity time graph, when we got a straight diagonal line, that is going to be our acceleration. So in this case, we'd have our straight line like that. So that's going to be acceleration, but on the distance graph, remember, it was a curve. So that's sort of the main ideas with the two graphs. So for this one that we just had here, we have a velocity change of 4 up, and our time is 4. So just like we did for calculating velocity, we can actually calculate acceleration the same way. So we can do rise over run, or velocity over time. So in this case, we did 4 meters per second over 4 seconds. So the way we write that is it would be 4 meters per second, or just 4 meters per second squared. Okay. Just like the last graphs, if the line is sloped downwards, so when we had our velocity graph like this, that was our positive velocity, and if we had a slope that was going downwards, that was our negative velocity. So the same sort of things apply here. In this case, we have an upwards acceleration, so that was a positive acceleration. So the next section that we have on there would be our downwards slope, so that would be a negative. So we could do the same thing. We could go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we got a change in velocity of 10 going down. And that occurred over 1, 2, 3 seconds. So in this case, then our acceleration would be negative 10 divided by negative 3, which is negative 3.3. So this one would be negative 3.3 meters per second squared. Okay, so that would be the last one. And then our very bottom part of the graph, again, you can see now it's a flat line. So just like where we started at 3 meters per second. The bottom is a flat line, so we'd be at 1, 2, 3, 4, 5, 6. So it would be at 6 meters per second, but it's now in the negative direction. So we just write that as a negative velocity, negative 6, and that's it. So velocity time graphs work a little bit simpler in some cases. The hard part is you need to remember sort of the difference between the two graphs and be able to solve either scenario. One last thing with a velocity time graph, let me just sketch one out here again. So let's suppose we started at a constant speed and then we had an acceleration down to 0, and that's it. So because these are velocity time graphs, there's one more bit of information that can be found by this graph, and that is displacement. If you think back to our formula, if we rearrange velocity equals d over t, we solve it for displacement. That would be the same thing as velocity times time. And if we think of a section on the graph, so let's just look at this first portion. So this portion of the graph, if we actually do the velocity, which is the height of the graph, which is 5, and we times it by the time, which is the length of the graph. So you can see basically all we're doing is we're getting the velocity times time would be like length times width of a rectangle, or base times height, or whatever you want to call it. So you can see in this case then, if we go 5 times 5, we get 25. So there's sort of a hidden section of the graph that we can get, and that is displacement. And basically displacement is just our area under the curve. So in this case, the area of the rectangle would be 5 times 5, so we get an area of 25 meters. So that would be our displacement. If it's a triangle like we see for the second part, do the same thing. So the triangle, you can see here now, we have a height of 5 still, we have a base of 5, but because it's a triangle, we'd have to go base times height divided by 2, which would give us 12.5 for our area. So the area for that triangle is 12.5 meters. So you only have to be careful if it's a graph, if it's triangles, make sure you cut that answer in half. And the reason for that is because we weren't going, even though we started at a speed of 5, we went down to 0. So if we average those out, we'd have an average of 2.5 meters per second for our speed over the 5 seconds. So if we do velocity times time, 5 times 2.5, that would give us the 12.5 meters. So each of those sections, we have those distances. So if the question was, what is your total displacement? So if we were trying to calculate the total displacement of this situation, we'd have 25 meters plus the 12.5. So our final answer would be 37.5 meters for that entire situation. And that's it. See you next time.